back to Shiksha. So today we're going to look at periodic functions. Today we're learning about periodic functions, and you're good at this when you can describe what are the key properties of periodic functions, when you can predict the future behavior of a periodic relationship when you're given a graph. To start off, I want to talk to you a little bit about Hopewell's Rocks National Park, and this is in New Brunswick. At Hopewell Rocks National Park, this is sort of what it looks like when you're down on what they call the beach. Notice how wet and muddy the ground is down here. And they have these fantastic, what they call flower pot rocks that are really heavily eroded at the bottom, but the top is fine. And the reason that they get shaped like this is over millions and millions of water cuts away at this. I'd be saying, hey, hold on a second. I don't see any water here. All I see is this ominous sign that says only go up here and only go down here. And there's a big transparent window here that says the beach access, is it open or closed? And lots of other warning symbols that tell you do not go down 3 hours before or after high tide. And make sure you're back, before the timer goes up. And otherwise, you could really be at risk that that is the case. The reason that the rocks are only eroded to here is that the tides change the height of the water a lot. At certain times, for example, high tide at 3:25 in the afternoon, the water is literally as high as here. And then by 9:43 a.m. the next day, it has gone down and exposed the entire beach. So what you're looking at here. Now, Nikki, my friend, finds this fascinating. She's decided to measure the height of the water every 2.5 hours, starting as early as she can, which is 5 a.m. So Nikki comes down and, well, she doesn't exactly put a ruler there, but she does have a way to measure it. At 5 a.m., water kind of looks like this. It's 2.5 meters above the ground here, above the sea floor. Eventually goes up a little bit. So after 2.5 hours, it goes up to 5.69 meters. After 5 hours, so this would be about 10 a.m. Oh, it has gone all the way up here to 10.52 meters above the ground. We're going to keep going. Well, after 7.5 hours, finds it actually has gone down a little bit. After 10 hours, gone down even further. After 12.5 hours, it has gone down almost to where it started originally. After 15 hours, it had gone up to 6.8. And then she keeps on measuring for the rest of the day. And these are all the measurements that she can come up with. We're going to try and figure out, is there a pattern happening here? To do so, I'd like you to pause the video and graph this data and see if you can use your graph to predict what the height of the water will be at these times. Now remember, Nikki started measuring at exactly 5 a.m. So I want you to copy down these axes, the number of hours after 5 a.m., the height of the water, and plot this data on this graph, and then unpause the video when you're done. Hopefully you saw that. Okay, let's take this dot and put it right there. That's 0 and 2.5, 5.69, 2.5 and 5.69 would be just about somewhere there. And I can keep doing this at every single point that I've got here, just plotting on the graph and noticing that the water level went up, but then it started to come back down. Then if I keep plotting the points, I'll see that, whoa, it actually started to go up again. And then come right back down. So, what would the graph look like, the height of the water hours after 5 a.m.? Well, if I was just trying to connect the dots here, and I invite you to do that right now, go ahead and pause the video if you need. If I just connect the dots here, I get something like this. Now, can I use this graph to figure out what was the height of the water at 5 p.m.? Notice that Nikki didn't actually measure that. She only measured it 12 and a half hours. That was at 5:30 p.m. That's 12 and a half hours after 5 a.m. If you look at the graph, notice that there's sort of like a pattern that repeats. The water goes up, comes back down, it goes up, it comes back down. And that seems to take exactly 12 hours. 12 hours for one cycle to repeat. Because I can measure, I can look at this and I can see, oh, that right there, that's about 24 hours. So one cycle must be 12 hours. Well, okay, if this starts to be a repetitive pattern, then if I want to find out the time at 12 at 5 p.m., can't I just start at 5 a.m. and go up 12 hours? That's exactly 12 hours after the time that Nikki started measuring. And in fact, I do see that at that point, the water is right back down to where it started, which was 2.5 meters. Now, if I want to see 7:30 p.m., well, that's not, Nikki didn't measure, she didn't measure that on her graph here. We have we have 7:30 a.m., which is 2.5 hours after 5 a.m. But we don't have 7:30 p.m. Can you figure out what the height of the water is at 7:30 p.m.? And at 7:30 p.m. the following day, even. Pause the video here right now and see if you can solve that. Hopefully, you realize that, well, if I could find out what time it is or the height of the water at 5 p.m. by looking at 5 a.m. and going forward 12 hours, can't I do the same thing for 7:30 a.m.? 7:30 a.m. the height of the water was 5.69 meters, and if I advance that by 12 hours, well, the water should end up back in the same position, right? This cycle just repeats itself. And so the height of the water should be the exact same it was at 7:30 a.m., which is 5.69 meters. Finally, what about 7:30 p.m. the following day? Well, the problem is I don't have any data for the following day. But if I assume that this pattern will repeat itself, that the water will go up and down because the tides work on a very similar pattern, well, then I can just take this and I can extend this pattern quite a bit. And not only do I have to now, not only do I know that the tides had brought the height of the water to 5.69 meters at 7:30 p.m. Well, 7:30 p.m. the next day would just involve going forward by 24 hours. And if I do that, I notice that, whoa, the height of the water is still just 5.69 meters. Wild. When a function creates a graph that actually has a pattern that is repetitive, we call this a periodic function because the period of a periodic function is basically how much does x need to change to complete exactly one repetition. And the reason that periodic functions are so useful is that if something does behave in a periodic manner, then you can actually predict future values of, the dependent variable by taking the values of the independent variable, which is usually x, and adding one or more complete periods. And we'll see an example of that just now. Example: Mausanram is a village in India that's special. It's believed to have the most rain. Planned for her trip in January 2025. What Pardeep has done is predicted that it's going to rain about 794 millimeters. So she's going to maybe bring her umbrella or her raincoat, but she has just made a prediction about that. And the way she got that was she took the monthly average rainfall. What mistake is Pardeep making? And how can we correct her so that she can predict the right amount of rainfall? Pause the video here and think about that and see if you can figure it out. What is the mistake she's making? Well, hopefully, you realize that, well, even though the average rainfall was about 794 millimeters, it probably didn't rain that amount every single month. In fact, it only gets rainy in India. I'm not sure if you know this or not, but it gets rainy around the June, July, August sort of months. That time that in the northern hemisphere you might call summer. Well, in order to predict the right amount, we can't just take the monthly average if that's the case. Because January, it might rain a lot less than this. we're going in July, we might need to expect a lot more than this. What we need is some data. We need to know what was the rainfall like exactly one cycle ago, one period ago. And because the weather changes on an annual basis, one on a yearly basis, data for an entire year. And looking at the data for the entire year, we can see that actually June and July have a ton of rainfall. January looks like relatively there's very, very small amount of rainfall. So maybe Pardeep needs to, doesn't need to quite pack away her boat or canoe just yet. And maybe she could get by with just a light poncho. Because the weather changes periodically and the period is every year, instead of taking the monthly average, of course, it would be much, much better to look at the average rainfall in just January of the previous year or any other years prior to that. That would give you a much better indicator of how much it's going to rain.
If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.